Hello friends! Can you imagine this Earth on which we humans have been born, this Earth which is home to innumerable species of living beings? This very Earth was a ball of boiling lava 4 billion years ago, a ball with no sign of life. This begs the obvious question, how did this ball of lava transform into the Earth we live in today? Where did water come from? How was the moon formed? These are all connected to the birth of our sun and solar system. In this video, let's understand these in depth. About 4.6 billion years ago, that is 4,600 million years ago, our solar system did not exist. Instead, there was only darkness. Deep, quiet, and empty space. In this space was a cloud full of dust and gas. This cloud is now known as the solar nebula. In Hindi, it is called Niharika. It contained various gases. Of them, hydrogen and helium were the most abundant. This cloud was peacefully traveling through the darkness of space for millions of years, then, suddenly one day there was a big explosion. And no, I don't mean the Big Bang, I am talking about the supernova. This explosion wasn't caused inside the cloud, it took place somewhere close to it. A dying star exploded near it. This kind of explosion is called a supernova, and it often happens to those stars which reach the end of their life. The shock waves of this explosion reached our solar nebula and caused gravitational instability. In some areas of this cloud, the gas and dust began compressing. Gradually, this entire nebula starts collapsing inward, and the gas and dust start revolving around it. The nebula looked like a rotating disk at this point. This flat, rotating disk is called the protoplanetary disk. Proto means before, the disk that existed before the planets were formed. As shown in the animation on the screen, this was what the disk looked like. Since this disk was flat, this helps us understand why our solar system is flat. I talked about this in the Voyager video. When the planets of our solar system orbit around the sun, they are almost on the same plane. The orbits of the planets aren't significantly higher or lower than the others. Now, at the center of this protoplanetary disk, the pressure and temperature kept on increasing and it gave birth to a protostar. Protostar means the same thing basically. The thing which existed before the star was formed. Gradually, the contents of the nebula were pulled towards the center due to increasing temperature and pressure. And at one point in time, the center became so concentrated that nuclear fusion reactions started. Hydrogen's fusion reaction. It takes place at around 15 million degrees Celsius. In this reaction, hydrogen turns into helium. Because of this fusion reaction, our sun was born. This reaction is still taking place on the sun and is the source of sunshine, heat, and light on Earth. The details of the actual reaction is quite complex, but broadly speaking, hydrogen is being converted into helium. Back then, 4.6 billion years ago, most of the gas and dust in our solar nebula was converging into the sun. This is why even today the sun makes up about 99.8% of the total mass of our solar system, and the remaining 0.2% didn't go unused. That 0.2% accounts for 8 planets, hundreds of moons, thousands of comets, and millions of asteroids in our solar system. But the question is, how did these planets start forming? That's so interesting. Small dust particles in the rotating protoplanetary disk started colliding with and sticking to each other. This happened due to static or chemical bonding forces, and initially, they formed into small clusters. Millions of years later, the clusters started getting bigger when more dust particles collided with them. Gradually, some of them got so big that their diameter ranged from 1,000 m to a few kilometers. These bodies are called planetesimals, a tiny version of planets. When gravity pulled these planetesimals together and their mass or size became as big as our moons, they were called protoplanets. The process of these dust particles accumulating together is known as accretion. Look at how accretion is defined in astronomy. The coming together and cohesion of matter under the influence of gravitation to form larger bodies. The accumulation of materials leads to the formation of larger bodies. This process of accretion was presented to the world by a Soviet Union astronomer Viktor Safronov in 1969. But back then, no one took him seriously. It was only in 1984 that Safronov's work was being studied, and his ideas were being adopted by the scientific community. Today, scientists have observed this process of accretion all over the universe through powerful telescopes. Astronomers have seen this happening in other solar nebulae, where dust particles accumulate quickly, and in just a few thousand years, they scale up to around 1 centimeter. Since this was observed in different stages, scientists can now confidently say that for millions of years, these small particles keep on growing, and eventually, become planets. Another proof of this process can be seen in meteorites. When scientists study the meteors that fall on the Earth to check their chemical composition, One of the things that have been found repeatedly is chondrules, small pieces of dust and rocks from the time before the formation of the planets. They contain radioactive elements like uranium and hafnium. It helps scientists find out the age of these bodies. By the way, another interesting fact is that the uranium found on our Earth is older than our solar system. It is considered to be 6 billion years old. This means that it was formed in some supernova. By collecting data from these measurements, scientists can come up with simulations of the collisions of dust and planetesimals. And these simulations help us estimate that it would have taken tens of millions of years for the protoplanets to form. Now talk about our Earth. These small protoplanets and planetesimals often collided with each other. These weren't small bumps. They produced a lot of energy. These generated so much heat that it melted rocks, giving rise to seas of lava. As these protoplanets collided with each other, they became bigger. Because of gravity, over time, they started becoming spherical in shape, and after numerous such collisions, our Earth was born. Over millions of years, gravity pulls these rocks together to form the Earth, one of at least 100 planets circling the Sun. During this period of constant collisions, small protoplanets or planetesimals would collide with our Earth frequently. This period is known as the Hadean Eon. The word eon means an indefinitely long time, and the name Hadean is derived from the Greek god of the underworld, Hades. I guess you've already understood why they chose this name. Back then, Earth was just like how hell is described. This was the time between 4.6 billion years ago to 4 billion years ago. Some objects that collided with the Earth during this period were as big as 100 or even 200 kilometers in diameter. Any rocks that existed on the Earth at that time would melt and turn into lava, being compressed repeatedly. But now comes the most amazing part. This hellish eon was the reason we have water on Earth. Some comets and asteroids that collided with Earth contained high concentrations of water in them. You might ask how those asteroids and comets got water. Friends, that was because of the solar nebula. The cloud of dust I mentioned earlier in the video contained ice crystals too. Even our Earth had some water. When the minerals trapped inside the microscopic crystals from the Eon period were analyzed, it was discovered that liquid water was present on the Earth as well, but the increasing water reserves on Earth was caused by the colliding asteroids and comets. Simultaneously, there was another process underway. During these collisions with the Earth, the water would become steam and go into the air, and after some time it would come down as rain. By the end of this Hadean Eon, our Earth had become a homogeneous ball. There was magma all around. The Earth had become almost like a uniform layer of lava, held together by gravity. This led us to differentiation.